profesor Roman Slowinsky, que viene de Polonia, y les voy a leer una breve semblanza de él. Es alguien muy conocido en investigación de operaciones y en general en el área científica. Esta es una muy breve semblanza antes de su plática. Él es profesor y el jefe fundador del laboratorio de sistemas para apoyo a la toma de decisiones inteligentes en la Universidad de Poznan, en Polonia, y también es profesor en el Instituto de Investigación en Sistemas de la Academia Polaca de Ciencias, que pueden ver el logo. Como miembro de la Academia Polaca de Ciencias, ha sido electo como su vicepresidente para el periodo 2019-2022. También es miembro de la Academia Europea y es fellow de varias organizaciones, incluyendo IEEE, IRSS, Informs y IFE. En su investigación, él combina investigación de operaciones con inteligencia artificial para la ayuda en la toma de decisiones. Ha sido European Chair de la Universidad de París en Dauphine, profesor invitado en el Instituto Federal Suizo de Tecnología de Lausana, de la Universidad de Catania en Italia, de Polytech Mons, de la Universidad de Michigan en Ann Arbor en Estados Unidos, de la Yokohama National University, de la Universidad Laval en Quebec, en Canadá, de la Universidad de Missouri, Colombia, la Universidad de Osaka, Polytech Tours, École Centrale Paris y muchas otras. Fue galardonado con la medalla de oro de Euro, que es el reconocimiento más importante que otorga la Asociación Europea de Sociedades de Investigación de Operaciones. La recibió en 1991, y tiene también un doctorado honoris causa de la Facultad Politécnica de Mons de Bélgica en el año 2000, de la Universidad de París Dauphine en Francia 2001 y de la Universidad Técnica de Creta en Grecia 2008. También es profesor honorario de la Universidad de Nanjing de Aeronáutica y Astronáutica de 2018. En 2005 recibió el Annual Prize of the Foundation for Polish Science, que es la distinción más elevada que otorga el gobierno de Polonia, y en 2020 recibió el Scientific Award del primer ministro de Polonia. En 2021 fue promovido por el primer ministro de Francia al rango de oficial de las palmas académicas. Desde 1999 es el editor principal del European Journal of Operational Research, que es una de las revistas más importantes y de mayor factor de impacto en el área. Y de acuerdo a research.com, es el computólogo más citado en Polonia y es el número 349 en el mundo. Es un gran honor que nos acompañe el profesor Slowinsky, que nos va a hablar de Preference Learning and Evolutionary Multiobjective Transition.
Thank you, brother. We are half in the morning, half afternoon. First of all, I wish to express my thanks to Professor Carlos Coelho for his kind invitation to your prestigious institute. I came here with Professor Eduardo Fernandez from the University of Sinaloa, and I'm very pleased to say that Eduardo was my first PhD student in Poland. He was graduated in 1987, and since then I had 26 other doctoral students, but Eduardo is one of the most important in my CV. So the subject of my talk, which I choose for today, is present PhD student in Poland. He was graduated in 1987, and since then I had 26 other doctoral students, but Eduardo is one of the most important in my CV. So the subject of my talk, which I choose for today, is preference relation. So forgive me some simplifications that are inherent to a lecture of a newcomer to this field. The plan of my talk is the following. So I will start with some background, and quickly I will pass to interactive evolutionary multi-objective optimization, and within this subject I will concentrate on elicitation of preference information and on model building of preferences from holistic preference information. And then I will inform you how the preference model is making pressure on the recombination procedure in the evolutionary algorithm. And I will pass to three main implementations that we made in such a spirit, so-called NEMO methods, XIMEA-DRSA, and CDEMO DCEMO based on some preference cones. And I will illustrate those methods along with some experiments, computational experiments on some benchmark problems. Those will be on continuous multi-objective optimization and on multi-objective knapsack problems. So, starting with the introduction, multi-objective optimization problem arises when you have a vector of objective functions, which are functions, real valued functions of some vectors of decision variables, and there is a set of constraints on the variability of these decision variables. There may be some additional constraints like integer values of decision variables or some combinatorial nature of such a multi-objective optimization problem. But what is very important at the end of such a formulation is that the only objective information which stems from the formulation of such a multi-objective optimization problem is a dominance relation in the set of feasible solutions. And let me remind you quickly what is Pareto optimal or non-dominated set of solutions. So a solution A is Pareto optimal or efficient or non-dominated if and only if there is no other solution B such that B would be not worse than A on all objectives, and on at least one objective it would be strictly better. So imagine that you have two objectives, F1 and F2, and they are to be minimized, and all dots here are solutions. So you see that the only interesting solutions of such a formulated problem are those black dots, which are non-dominated Pareto optimal solutions, which create so-called Pareto front. And on this front, you have some solutions which are easily attainable, which are supported Pareto optimal solutions, and those which are lying not on the convex envelope of this Pareto front, which is called non-supported Pareto optimal solutions. And you have also some reference points in this space, which are often used in the optimization procedures, like ideal point, which is inheriting the coordinates of the best solutions on each individual objective, and nadir, which is inheriting the coordinates of the worst solutions, worst coordinates of the best solutions on individual objectives. So, evolutionary multi-objective optimization algorithms have shown remarkable effectiveness in approximating the Pareto front. And this happened at the beginning of this century, especially for multi-objective combinatorial optimization problems. Those techniques appeared to be very efficient. So it attracted a lot of attention. Also because those problems are particularly hard computationally. Those problems are computationally intractable for two reasons. First, they are NP hard, even if their single objective optimization problem is P complete. So this is the case, for example, of spanning trees or mean cost flows, which in the single objective versions are easy problems, but with multi-objectives they are becoming NP hard. And also the listing, the searching for all non-dominated solutions is also P hard. So for those two reasons, to solve those problems in an exact way is an intractable endeavor. However, visualizing a Pareto front is problematic, especially in case when you have more than 2 dimensions. And in case of 3, 4, 5 dimensions, this is hampering the decision maker in choosing the best compromise solution. So, until some time, there were techniques that were reducing the multi-objective problem into single objective problem by synthesizing a priori all the objectives into one objective. And then the problem was solved as a single objective programming problem. So you see that, of course, the a priori specification of preferences is not easy. In this case, people proposed to repeat calculations with different parameters if the selected most preferred solution was not satisfactory. Another way was just by approximating the Pareto front and then reflecting on the approximation of the Pareto front, which is the best compromise solution. But as I said, in case of more than 2 objectives, so this is not an easy problem. So the idea came then from interactive multi-objective mathematical programming that it is maybe wise to take preferences from the decision makers in course of the search of the approximation of the Pareto front, and then to limit on a limited part of the Pareto front, taking into account the partial preferences, and step by step to arrive to the most compromised solution by specifying more and more the preferences of the decision maker. And this was a conclusion of a set of researchers who gathered many times in a German place famous for seminars of people in computer science but also in operational research, which is called Dachstuhl. And this is the place where we met for the first time in 2004, I think. And the specialists from all over the world discussed how to use the experience of people who were working already in the end of the last century on interactive mathematical programming with multiple objectives and the new experts of evolutionary multi-objective optimization. And the result of this group was a book on multi-objective optimization, interactive and evolutionary approaches, which was finally finished after the third meeting in 2008. Professor Coelho is author of one of the chapters on parallel computing and multi-objective optimization. So, in fact, this meeting and this book triggered a new trend in multi-objective optimization, especially in its evolutionary optimization part. In the interactive evolutionary multi-objective optimization, the preference elicitation phases alternate with optimization phases. And in the preference elicitation phase, the decision maker is getting asked to express her preferences on a small subset of non-dominated solutions, and then those answers are like critics, which is preference information. They are influencing the computational phase, where the optimizer is trying to satisfy the expectations of the decision maker as is providing a new set of candidates for the best compromise. And again, the new iteration starts with the critics of the population presented to the decision maker. Those critics are converted to the preference model that is influencing the optimizer and so on until the best compromise is found, or there is a statement from the part of the decision maker: for this problem statement there is no compromise. So you see that this is an iterative process in which humans are in the loop. And as humans are in the loop, so the question is, who is learning? And the answer is both. The model is learning the preferences of the decision maker, but also the decision maker is learning the problem and the shape of the Pareto optimal set. So this is a mutual learning. In such a case when a human decision maker is in the loop, it is very important that the decision maker understands the impact of her preference information into the direction of optimization convergence. This is very important for so-called psychological convergence of the procedure, because the decision maker should become convinced that the preferences built during subsequent iterations are properly represented and used in the optimization phases. So we will come back to this issue of explainability also later in some methods. So we have to agree in what way the preference information will be provided by the decision maker in the course of this interactive procedure. Should the decision maker provide direct or indirect information? The direct information concerns directly the parameters of an aggregation procedure, because of course in multi-criteria decision making and also in multi-objective optimization, always the issue is to aggregate the multiple dimensions into a single dimension so as to get the best compromise solutions. So should we ask the decision maker to provide exact information about parameters of the aggregation function, of the aggregation procedure? So this is not easy. So when we come back to the beginnings of multi-criteria decision making, to the works of Peter Fischberg, so already in 1967 he described and classified 24 methods of estimating additive utilities. So additive utilities are the easiest aggregation of the multiple dimensions. But even in this way, in this case, the elicitation of preferences is not easy. So the decision maker, in order to provide the weights or the shapes of marginal value functions, has a problem. And leaving the decision maker with this problem is exhibiting the decision maker to the risk of oversimplifications, and then to the fact that at the end the decision maker will not get the expected best compromise. So maybe not directly, but indirectly. Because why the decision maker is not easy with the preference information concerning the weights or the shapes of marginal utilities, maybe the decision maker is more easy with, for example, holistic pairwise comparisons of some solutions, yes? Like decision examples in artificial intelligence. Indeed, so this approach to multi-criteria, also decision making, is now prevailing. Because decision examples are relatively easy preference information. Decision can be observed also without active participation of decision makers. Yes, we can observe the behavior of customers, of users of different tools and products, and from this use we can guess what are the preferences of the decision makers. Also, psychologists confirm that decision makers are more confident exercising their decisions than explaining them in terms of parameters of an aggregation model. The related paradigms are in economy. You know Samuelson already in '38, he wrote about preferences of consumers which can be revealed by their purchasing habits. Also in artificial intelligence and machine learning we have the paradigm of learning from examples. knowledge discovered. It is also from holistic preference information. So the conclusion is indirect elicitation of preferences is more user-friendly. And how it could look like in the case of multi-objective optimization. So these can be pairwise comparisons of solutions characterized by some vectors of values of objective functions. For example, this decision maker would prefer such a profile of a student than another profile of the student. Or in the case of classification decisions, there could be examples of typical profiles of students for bad class, typical profiles of consumers for a good class. There could be also information about intensity of preference, but not necessarily cardinal, like some methods require. For example, here A is preferred to Z more than C is preferred to K. So this is an ordinal expression of the intensity of preference, which is quite realistic. Or a ranking of some reference solutions. For example, in this sample, I see that F is the best, D is the second, E is the third, etc. So these are examples of preference information items expressed by the decision maker in such a holistic approach. Now, to remember you, what are the possibilities of aggregating multiple dimensions? Historically, the first was multi-attribute utility theory. And it is proposing to use a value function. A value function is aggregating all the objectives, criteria, so here G is a criterion, and there could be weighted sum involving just the weights multiplied by the performances on criteria, or this could be more advanced general additive value functions, or in case of interactions between criteria, in case of cardinal criteria, Choquet integral, and in case of ordinal scales of criteria, Sugeno integral. But all of those end with a score of a solution, of an alternative, and this score is ranking the candidates for some solution. The second idea of aggregating multiple dimensions came from France. And it is so-called outranking relation, which is aggregating indifference, weak preference, and strict preference. And you would say, okay, so this is a poor relation. However, when you construct this relation for all ordered pairs, AB and BA, you can guess about large preference, indifference, and incomparability, which is not possible with the value function. And the third method is by decision rules, and which came when the machine learning era came into play, and there are different syntaxes of the rules for classification, because in case of classification you have just to compare the profile of an alternative, of a solution, with some thresholds which are discovered by induction in order to conclude about the membership of an alternative in the class. In case of ranking and choice, you have to take into account pairwise comparisons between the competitors, because the position of an alternative in the ranking depends on the quality of its competitors. So you need to have in the syntax of the rule pairwise comparisons, for example, like here in the case of cardinal scales, that A is better than B on criterion I in degree at least HI, on J in degree at least HJ. And these HJ, like those thresholds, are discovered by induction during the learning process. And the conclusion is a pairwise comparison. A is outranking B. So we proposed, together with my former doctoral student Salvatore Greco, this kind of models for modeling preferences. And there was a question, okay, but how this model relates to the others? And it is not easy to prove which model is the best. But when you come down to the level of axioms, of the most basic assumptions that you have to satisfy in order to build the model, then you can prove that the most general is the rule model. And the other models exist if and only if there exists the decision rule model. So this model has the greatest capacity of representation of preferences. The most complex interactions, even those that Sugeno integral or Choquet integral are not able to represent. And there are proofs for that. So this is why in one of those methods we are using decision rules as a preference model. Now the question is how complex should be the preference model in our multi-objective optimization course. If the model is too simple, then it is not able to represent preferences. And imagine that step by step in the course of the interactive procedure, the decision maker is providing new pairwise comparisons of some candidate solutions. More and more, it is difficult to represent those pairwise comparisons with a simple model. For example, if we use a linear model, such as two pairwise comparisons that green is better than red are not able to represent with a linear function. So no linear function will represent those two pairwise comparisons. But if you choose a big gun from the beginning, a very general model, then it is very difficult to enrich such a model, and you need a lot of preference information to get the model that will say you more than the dominance relation. Just. So you have to be careful about choosing a proper complexity of the aggregation model. And now the question, in which point of the evolutionary algorithm the preference model plays some role. And I am presenting here the very known scheme, well known for you, of recombination, and where you see that the set of parents is ranked by the preference model. And this is the place where the preference model is making a pressure on the recombination. Yes, so the preference model of the resulting ranking of solutions in the population makes a pressure because it is directing the evolutionary optimization towards the most interesting part of the Pareto front. So with this in mind, I will present now the first kind of methods, which are called NEMO, and they were built on the very popular in that time evolutionary multi-objective optimization algorithm, NSGA2, by Kalyan-Moy and Kalyan-Moy-Depp and co-authors, who also attended our Dachstuhl meetings. So in this NEMO procedure, we proposed to ask the decision maker every Q iteration to compare pairwise some non-dominated solutions in the current population. And from these pairwise comparisons, we are building either a linear value function, which is reconstructing these pairwise comparisons, or general additive value function, which is doing the same, or Choquet integral, or even more complex value functions. So the interactive procedure in this case is looping, and you see the inflow of preference information here, pairwise comparisons, and here the so-called robust ordinal regression, which is building all compatible value functions compatible with this preference information. And those compatible preference models are influencing the optimizer, which gives a better set of solutions in the next iteration. So the idea comes from a multi-criteria decision aiding method, which we proposed together with Salvatore Greco and Vincent Mousseau in 2008. And the idea of this methodology is such that, for example, if you have to make a multi-criteria decision on a set A of alternatives, a big set, thousands of solutions or alternatives. So it is assumed that very often the decision maker is able to compare pairwise a small subset of those alternatives. And this is the preference information given by the decision maker. So the task of the mathematicians is then to find models, and in this case, for example, additive general model, which will reconstruct these pairwise comparisons. However, to find not only one instance of such a model, but all instances of this preference model which are reconstructing this preference information, and to use them all on this whole set A. And then you are getting two kinds of preference relations in set A. Necessary preference relation, which is true for all instances of the preference model, and possible preference relation, which is true for at least one instance of the preference model. And in this case, even if the value functions, the marginal value functions are general additive, just monotonic, the procedure for getting such a whole set of compatible instances is based on linear programming. So quite easy to manipulate. And here I am giving you a very short workflow of this procedure. So at the entrance we have preference information. Then for preference information we have such a zone of possibility of the marginal value functions compatible with these pairwise comparisons. And then we ask how are the necessary preference relations. So of course we will reproduce all the pairwise comparisons from the original set of pairwise comparisons, but also some other alternatives will compare necessarily in such a way that A will be preferred to X. And what happens when you add a new preference information in new iteration? So look, what happens? New information items comes, and the area of possible marginal value functions which are compatible with the preference information is decreased, is constrained. And more pairwise relations are necessary in the set of all alternatives. So this necessary relation would be dominance relation if there would be no pairwise comparison at the entrance, and it is becoming richer and richer than dominance relation when the pairwise comparison are appearing at the input. So this robust ordinal regression works in a loop, and we call it this preference elicitation with constructive learning. And there is a big analogy with preference learning in machine learning. You know that in machine learning, which developed without any respect to the order in data, people came to conclusion that, attention, yes, we have to pay attention to the order that is inherent to data, because otherwise we come to wrong conclusions, to stupid conclusions. And in this way, preference learning was born. However, this is a non-statistical way of learning preferences. We characterize this robust ordinal regression in preference learning and ranking in a machine learning journal publication. And here you see why it is robust. It is robust because it takes into account partial preference information, and it is looping in this way. So now, very quickly, I will pass to characterization of our three NEMO methods. Then I will pass to the method which is using decision rules as preference model, and I will end with the method which is using as preference model preference cones. So we released 3 versions of NEMO. NEMO 0, NEMO 1 and NEMO 2 Choquet. The first is using a representative compatible value function from all possible value functions, and it is ranking solutions in each non-dominated front of NSGA2. The second, NEMO 1, is replacing dominance relation with necessary preference relation. So it is richer than dominance relation. And in this way we get fronts which are not only non-dominated but also which are not necessarily dominated. And in the NEMO 2H we are using a combination of linear value function and Choquet integral in order to adapt to the complexity of the input preference information. And I will show the details a little bit later. So let me remind the idea of NSGA2. It is based on dominance ranking. So when you have a population, this population is divided into fronts of non-dominated solutions. So here blue will be the first front and red will be the second front. And within the same front, Depp is proposing to rank the individuals with respect to the crowding distance so as to prevent sticking too much of similar solutions. And then he is arriving in this way to the representation of the whole Pareto front. So this method worked for many years. However, it appears that it is not efficient for multidimensional cases. And somehow, like 8 years ago, Depp proposed a new version of NSGA2, NSGA3, which is dealing with multidimensionality. And how we adapted this idea of non-dominated front in the preference information case. So, in case of NEMO, we are ranking the solutions in each non-dominated front using the representative value function, compatible value function. So here you have the order of solutions. In case of NEMO 1, we are replacing dominance relation with necessary preference relation. So we have, in fact, smaller non-dominated fronts. And within the fronts, we are ranking the solutions with respect to crowding distance, but the crowding distance is not defined in the original space of objectives, but in the space of utilities, which is better because it is normalized to 0, 1. And finally, NEMO 2 puts in each front solutions that are preferred to all others in the population for at least one compatible instance of the value function. So if you would compare the fronts of NSGA2, so it is the largest because NEMO 1 has a smaller, or at least the same as NSGA2, and NEMO 2 has yet smaller. So information about the fronts is coming to the recombination procedure. So you have the fronts according to NEMO 0, NEMO 1, NEMO 2, and then in case of dividing the population into halves, so we can use here the crowding distance ordering, like here shown with this cubist. But later we came to conclusion that using one single model in NEMO is not reasonable because it is better to use a simple model at the beginning of the interactive process and then to use a more complicated, more complex model as far as some more complex preference information is incoming. So we start with linear value function, and every Q iteration we ask the decision maker to compare two non-dominated solutions. And then we put in the first front, as I said, solutions that are preferred to all others in the population for at least one compatible value function. We delete those solutions from the previous front from the population and create the new front, etc. And then we switch to two additive Choquet. Yes, you know that Choquet is permitting to take into account interactions among all possible objectives. But in this way, the model is very, very flexible. So this means that it needs a lot of parameters. Very often in such a modeling of preferences, it is enough to take only interaction in pairs of objectives. It is called two additive Choquet integral. Choquet integral, I think it is known to you, but in case not, so I will say that it was proposed in multi-criteria decision making in case where we want to underline some interactions in the sense that, for example, single objectives are very important, but taken together, not necessarily so important. For example, you are qualifying candidates to computer science faculty. And of course, for you, mathematics and physics are very important. So as single criteria, they will be 45% each. And literature is not so important in this context alone, because only 0.3 maybe. So if you would then think that mathematics and physics together should be 0.9, so this would in fact practically eliminate literature. So as a decision maker, I could think, okay, so people good in mathematics are also very often good in physics. So it would be a little bit redundant to consider both of them as important as the sum of their weights. So let's take that mathematics and physics will be only 0.5, and mathematics and literature will be 0.9. But this calls for the use of other weights. And this calls for the use of Choquet integral, that is using capacities instead of weights. And capacities are representing weights of single criteria and pairs of criteria, three criteria, etc. So the synergy can be positive in the interaction or negative in the interaction. Yes? And in this way, Choquet integral is representing better our preferences with respect to such interacting criteria. The formal formula of Choquet integral for a vector, imagine that this is a solution getting value f1 to fn. So this is a weighted sum with a capacity dependent on a subset of criteria, which is the subset of criteria in the permutation from the beginning to the ith criterion, ranked from the best to the worst. And in the positive interaction, so the capacity of the sum of subsets will be greater than the sum of capacities of a single subset. And in the case of negative interaction, redundancy, so the sum is smaller than the sum of individual capacities. I am explaining my students, excuse me to be considered as a student, but maybe it is not bad to transmit to you these examples for your students, that weighted sum is playing like that. So one remark more, that Choquet integral needs that all objectives or criteria are on the same scale. So first you have to normalize the criteria scales from 0 to 1 or from 0 to 100. And then in the weighted sum regular case, in the case of such a solution that would have those values on 4 objectives, the weighted sum is just the sum of the heights of the bars multiplied by their weights. So the capacities are dependent only on individual objectives. In case of Choquet integral, you are reasoning in a different way. So this yellow level was attained by all four objectives. Then the green level was attained by F1, F2, and F3. The violet level only by F1 and F3, and the red by F3. So you are using capacities like weights for all four, but until the yellow bar, for those three for green bar, for those two for violet bar, and for this one F3 for the red bar. And you are adding this all together, and this is giving the score of Choquet. Yet more interesting representation of the Choquet integral is the Möbius representation. Möbius representation is permitting to represent the capacity as a sum of individual weights of criteria, of objectives, plus the sum of weights responsible for the interaction. In case of two additive capacity, we have interaction only for pairs, IG. There is a requirement for monotonicity and normalization. However, the form of the Choquet integral for this Möbius 2 additive representation is easier to read, to represent, because it has a component responsible for weighted sum, plus the component responsible for the pairwise interaction. And why it is interesting in multi-objective optimization? It is because the isoquants of such a two-additive Choquet integral are represented by those two wings. This is for the weights equal for F2 and F1. And the angles of those wings depend on the weights used. And if you have the weight N12 negative, you can model the negative interaction. If it is possible, you can model the positive interaction. So the wings are bending either concave or concave or convex. So this is very convenient because it is more than, for example, such a Choquet integral. In fact, not Choquet, but the well, it will come to my mind. But this great capacity of modeling Chebyshev function. Chebyshev function is also permitting to change a little bit the wings of the isoquant, but not to bend it convex and concave. And two-additive Choquet is able to do it. So, in this case where you are not able to represent the preferences of the decision maker using a linear function, you are able to do it with the Choquet integral. And the Choquet integral has moreover the advantage of being in a special case just a weighted sum, or it can be also ordered weighted average. So the so-called OWA, very famous now integrator, or minimum or maximum operator. So this is really a very, very universal tool for aggregation, which is worth considering. And as you can see here, what was not possible with linear separator, it is possible with such a band Choquet integral to additive Choquet. And if there would be, for example, some need for displacement of this isoquant, you can change the weights and also use this, this separator for green and red. The problem for checking if there exists a model compatible with the decision maker's preferences for which X is preferred to all other solutions is for fixed weights a linear programming problem. And if for fixed weights you are not finding the compatible value functions, then you can make the weights free, and then you have to use the Nelder-Mead simplex method because it is becoming, because of those products, a little bit more complex, but still easy to solve. So now the promised experiments. And here I have to go quickly. So the experiments were done on the benchmarks. And in such experiments, you know well that because a real decision maker would be exhausted during such 50 runs of experiments, so we are using an artificial decision maker who is supposed to answer the pairwise comparison questions using some value function he or she has in mind. And we are assuming that the decision maker is reacting to our questions using a Chebyshev function. And the Chebyshev function may have different weights. And we compare our versions of NEMO with the single objective evolutionary algorithm that knows the true user's value function. So this is a comparison with evolutionary algorithm that knows what other methods compared do not know. So the results are averaged over 50 replications, and you see here the result. This convergence curve, this orange one, is of the benchmark algorithm single objective that knows the true value function of the decision maker. But then what you have good is this line, which is NEMO 2 until that point with linear value function. And if you would continue with linear value function, so it is not able to represent the preferences, and the red line is oscillating. However, when you switch in this point after iteration number 100 to Choquet integral, to additive Choquet integral, it is converging very close to the benchmark. We used also this methodology to multi-objective knapsack to show that it also works in case of combinatorial multi-objective optimization. So the difference between single objective knapsack and multi-objective knapsack is very well known to you. So we have to maximize many profits, p profits. And permutation of items is here a chromosome that evolves. And our artificial user has again a Chebyshev function as a true value function. And we are comparing NEMO 2 with linear value function and with Choquet integral with the benchmark, which is the single objective evolutionary algorithm, with the known true user's value function. And so the decision maker is answering questions, which solution of the two is better for you? And this answer by the Chebyshev function will be that this solution is better than this one. For another pair, again, the Chebyshev function will say this solution is better than this one. And now we have to find a preference model that will fit to those pairwise comparisons. So no Chebyshev function will fit it. Only, no linear function will fit it. Only two additive Choquet, like here in this case. And the result is that this two additive Choquet is giving a result even better than the benchmark solution. If I have 5 more minutes, excuse me. So this is our new proposal, which is called XIMEA-DRSA. So in this idea, the new type of holistic preference information is provided by the decision maker in this way that every Q iterations, we are asking the decision maker to classify K solutions from the current population into good and bad, into promising and not promising. Yes? So this is a relatively easy answer. And then from these classification examples, we are inducing rules explaining class good and explaining class bad. And for this we are using a dominance-based rough set approach. Why we are using a dominance-based rough set approach? Because dominance-based rough set approach has been proposed for pre-processing of classification examples which may be inconsistent. What means inconsistency in case of multi-objective optimization? It arises when a solution which is dominating another solution is considered worse. And why it may happen in multi-objective optimization? This is because the decision maker may not only look at the performances on the objectives, but also at the solutions themselves in the decision space. And because the representation of solutions in the objective space is not perfect, sometimes some objectives are missing, a decision maker may say, okay, I prefer this solution A to solution B. However, in the objective space, B will dominate A, and this will be inconsistent. So in order to deal with that, we are using the dominance-based rough set approach, which is permitting to discover the inconsistent part of the preference information. And why we are advocating for this approach? This is because, as I said, the decision rules is a set of decision rules is a preference model which is the most general. And also it is a non-compensatory model. It is accepting ordinal scales without converting them into cardinal scales. Very often methods require that the scale is cardinal. The very popular AHP method is requiring that all criteria are on cardinal scales because they require the decision maker is expressing the cardinal intensity of preference. So this is a violation of the introductory assumptions about the method. And also rules are easy to interpret because each rule is a scenario of a causal relationship between evaluations on a subset of criteria, of objectives, and a comprehensive judgment. So they are easy to be interpreted. And I am giving here you a very didactic example of the preference information given by the decision maker. So the decision maker is getting the 8 solutions and is asked to say which one is promising, good, and which one is not promising, bad. So let's assume that the answers were like that. So if we would apply the dominance-based rough set approach, we would see that there is inconsistency between x8 and x7. Because x7 is judged as bad, x8 as good, however, x7 is dominating x8. So what is certain in this information is this lower approximation of the class bad and the lower approximation of the class good. With this structuring of preference information, we can pass to induction of the decision rules. And the decision rules, first, certain decision rules, which are induced from the lower approximations, are 3. 2 rules underlying the bad solutions, and 1 rule underlying the good solutions. And you see here, those rules are never incognito. They are identified by the solutions that are supporting those rules. Of course, we could be satisfied not with certain rules, but with possible rules. And that we would have other 3 rules. However, the syntax, the conclusion would not be that certainly bad or certainly good, but possibly bad, possibly good. So we have the possibility of using certain rules or possible rules in the further steps. What are those steps? So here we assign solutions to ordered non-dominated fronts. So we are creating non-dominated fronts like in NSGA2. And within each front, we are ordering the solutions according to the score, which is the result of the matching good rules and bad rules. So good rules are scores in favor, and bad rules are scores in disfavor. And of course, rules are accumulated during the interactive process, and all rules are losing a little bit their importance. So there is an aging effect of rules. So with the time, the old rules are less important than the young rules. So all this makes that each solution in the population is getting a score, which is a numerical value permitting to order the solutions in the non-dominated front. And this is influencing the recombination. And also the scoring is permitting to have this controversial F3. And then we made an experiment which consisted in the same principle as before. Here we are asking to classify 6 or 8 solutions every 10 or every 20 iterations, and we are comparing such a XIMEA-DRSA method with a NEMO-2 Choquet, and also with this benchmark evolutionary algorithm which is using the true value function of the decision maker. And the results were replicated 50 times, and you see that the XIMEA is dark green, which is very close to light green, which is NEMO-2 Choquet, and it is attaining a very good score, and much better for 8 solutions asked every 20 iterations and 6 solutions asked every 10 iterations. So the experiment was much larger, of course, and I must say that it was quite satisfactory. Even for a knapsack problem, it gave a better result than the benchmark. But I would like to draw your attention 1 minute on the explainability. Why decision rules are good in modeling preferences in multi-objective optimization. And I am taking an example of 2-dimensional knapsack problem with 100 items. And we are asking the decision maker every 25 iterations to classify 6 solutions into good and bad. And from this preference information, we are inducing decision rules using the DRSA to explain the judgments of the decision maker. Let's illustrate the situation after the first iteration, after the iteration 101, and almost the end, 576. So the 6 solutions submitted to evaluation after the first iteration are those, and they are classified into good and bad. After 100, those solutions, bad and good. After 576, those solutions, good and bad. So now we induce rules. After the first iterations, the rules are not so interesting, because rules are based on single objectives, and the conditions are quite evident. So this is the shape of the Pareto front that we will see at the end. So of course the method does not know it. And we have to say that the rules are, however, interesting because they are not anonymous. They are supported by some examples. And the decision makers see that, okay, so because he gave x1, x2, and x3 good score, then such a rule was possible to be generated, and it is based on a single condition. So the decision rules are not anonymous. They are transparent because they are playing with a subset of objectives in the condition parts. And the decision makers, step by step, understands in what way there is going the convergence. And we would compare this process into the Kahneman's system of 2 ways of thinking. So the rules are like system 2 of reflection, of analysis, and system 1 is this spontaneous pairwise comparison provided by the decision maker almost not consciously. So here, after the iteration 100, the rules are more and more interesting. all rules are supported by some solutions, and you see the rule 101 is showing a subset of solutions. When we blow up this area, we see that after 576 iterations, so we have already a smaller subset of solutions, which is indicating only 8 solutions of the knapsack problems, and among those solutions there is the best compromise. So here is the situation at the iteration 600. In this iteration, the rules which are evaluating the solutions in the population, so these are all historical rules that accumulated in the register. And they are giving scores to candidates, and if we take the solution X with such coordinates, it is matching those red rules. It is not matching any bad rules, and it is indeed getting the highest score, and this highest score is even indicating the true user's best solution. So this is the CIMEA method. The only method that I will not be able to present is the method based on preference cones. So this is a method which is interesting because of his simple idea. The idea is that we are referring always to some good point called reference point, to which we would like to find our best compromise the closest as possible. And you know that for evaluating this distance, an achievement scalarizing function has been used. So this is this achievement scalarizing function. And its isoquant is also interesting, as I mentioned, but not as interesting as to additive Choquet. The wings are such, yes? And the wings are functions of the rho parameter and of the lambda weights. Such achievement scalarizing functions were used also in the NSGA3 method. It is using the concept of uniformly distributed reference points and corresponds to reference lines, which guide the evolution in the objective space. So the ultimate goal of this method by Karian Moideb is to generate a population in which for every black point here there is a solution lying close. So these black points are attractors on some hyperplanes, and this permits to have a uniformly distributed approximation of the Pareto front in the case of objectives which are more than 2. However, a very interesting idea is based on using the cones which are defined by the reference line of the achievement scalarizing function. Look, that just this remark, and I will finish with 2 other slides. So the decision maker has to decide in some iteration if A is for him or for her better than B, or vice versa. What does it mean if you use achievement scalarizing function? So this means that if the decision maker would say, I prefer B to A, so this would mean that B to A is equivalent on this direction of the achievement scalarizing function. If you would move a little bit this achievement scalarizing function inside this cone, then there would be a difference of B over A. So this means that all achievement scalarizing functions with the reference line going this direction will be consistent with B better than A. And B better than C or C better than B, for example, B better than C is another reference line, and both are going towards them. So this is creating in a natural way a cone. And within this cone, our solutions are interesting because they are compatible with this preference information. So, in fact, all directions within these cones are compatible with the preferences of the decision maker. And we propose to use this information to rank the solutions in the dominance fronts of NSGA2, and we got a method which is converging very fast. And also, in case of 2 dimensions, we can even observe the convergence speed. So, to end with my presentation, I would like to say that preference-driven EMO algorithm combine the search of solution space with user's preferences. And I think it is a future of multi-objective optimizations, because the decision maker has to be involved in the search process. And also not only examining solutions in the objective space, but also in the decision space. Our first applications were concerning the design of a reactor for production of polypropylene. And it showed that also CIMEA and this last method were quite well accepted by the decision makers. Thank you very much for your attention. I also acknowledge the contribution of my cooperators. Thank you very much for your patience.
So we have time for some questions.
Professor, how much sensitive are your methods concerning the increment of the number of objective functions?
So the objective functions may change completely the formulation of the problem. So this is what I said about the inconsistency. Yes, but sometimes you are not able to express analytically all points of view. This is why I'm mentioning that also evaluating of solutions in the decision space is very valuable. However, it may lead to inconsistency in the objective space. And then you get some inversion of dominance and you say, okay, why there is such inversion? Because some objective is missing. But now, how to introduce this missing objective? I cannot say exactly. So it is better to continue with this method and only possible rules instead of reformulating the problem. But the sensitivity may be small, may be big, depending on problem formulation.
Well, if you want to...
Yeah. Thank you very much for this interesting talk. I have some questions. Can you go to slide 19? That's fine. So, if I got it right, you transform indirect decisions to direct ones?
No. Into the model.
Yeah.
So I'm discovering what are the marginal value functions which would reconstruct this pairwise comparison.
Yeah, but you get, well, it's the other terminology. You get out of these discrete data, you get a global model.
Yes.
Using LP and this Choquet thing, right?
Here only LP.
Okay. So 2 questions. One of them is, what happens if you have maybe 2 decision makers and the data is inconsistent?
Okay. So we consider such problems. And of course, so in case of 2 experts, you may have 2 approaches. Either those experts are experts of the same space of solutions and their preferences are synthesized together. So I am adding the pairwise comparisons of one decision maker and the other. Of course, if one decision maker will say A is preferred to B and the other B is preferred to A, so there is no function which will reconcile such information. And the second is that we perform the calculations for each decision maker individually. And then we show the necessary preference relation for one decision maker and necessary preference relation for another decision maker. And we are looking into space of agreement and space of disagreement and we are asking additional questions which may reconcile those two decision makers. But it is not sure a priori that those decision makers will agree. So we consider such cases where we say, okay, if the decision maker 2 will resign of these pairwise comparisons, there will be no conflict. And, but it depends on the application. Maybe the decision maker is very close to this information and would not. Thank you very much, Carlos. Thank you very much for your attention, for coming. So this is the end of holidays, but usually the behavior of people is smooth. They adapt to hard work only some days later, and you are coming the first day of the end of holidays, so I appreciate it.
You look very enthusiastic.